So occasionally when we are working with one of these solids of revolution, we will require multiple integrals to set up an integral expression. And what I hope is that this will remind you of those problems where, I would say, find the area, between, find the area of this region here, where there are two different functions. Let's say this is the function f and this is the function g. We have to have one integral set up between here and here, because that's where the f function is being used. And then we need another integral between here and here, because that's where the g function is being used. It's exactly the principle that's being used for these problems. And I've got one of them lined up, so we'll take a look at that one. So I say let R be the region in the first and second quadrants shown below. So it's basically this region here. That's bounded by the functions x equals 1, so that's this guy, and cosine x, that's this one. And I want to write an integral expression for the volume of the solid generated when that thing is revolved around the x-axis. Right? So step 1, as it has been for the past several videos, is what is the thickness? Is this a dx or a dy integral? So either pause the video and answer that, or answer it for yourselves. It should be dx, because I'm revolving around the x-axis. If you ever revolve around the x-axis or any other horizontal line, you're going to be using dx. Okay? Step 2. What is the radius of the revolution? And what I had said before was that we always want to draw from the axis of revolution perpendicular up until you hit the function. And so there's our radius. But you'll notice that radius only works on this interval, right? Because that's the place where I'm using this function, right? Over here, I would have from the axis of revolution up to this function, right? And I'm going to use that between here and here. So the idea is, because there's a different function being used on top in different places, I'm going to need multiple integrals. I'm going to need multiple things set up, right? So my green radius, the part over here on the left, this part is going to be, as I mentioned in the previous video, the top, x plus 1, minus the bottom, okay, which is 0. I suppose it doesn't matter. I'm going to go and write it in anyway. X plus 1 minus 0, just so we get used to the idea that radius is always the distance between two different functions. And then that nice pretty purple color we've got, I'm looking at the difference between the top function cosine x and the bottom function, which is 0. So the purple one is cosine x minus 0. Right? Again, just showing that there's a top function and a bottom function. Okay. Now that I've done that, we go on to the third step. Right? Our third step is supposed to be bounds. And part of the reason I've classified this as two different colors is that there should be different bounds for each one of them. The green set of bounds is fairly simple, because you can tell that it starts at -1 and goes to 0. Right? So these green bounds, -1 to 0. The purple ones start out easy, because we know we have to start at 0, and we go until whatever this value is. Right? And so we'll take a minute and consider that. What's causing that? What's causing that value right there is the x-intercept of the y equals cosine x function. So the way we find x-intercepts is by plugging in 0 for y. So I'm looking at where is 0 equal to cosine x. So that means what angle has a cosine measurement of 0? And that's going to happen, if you remember your unit circle, it happens with pi over 2. So this second integral is going to be from 0 to pi over 2. Right? The last step, the step 4, is where we actually write out what the integral is. Right? And again, I'm going to have two different ones. They're going to be added together. So first, the green one, I have pi times the integral from -1 to 0 of the radius. And at this point, I'll simplify this and just say, look, I understand it's just x plus 1. This is x plus 1 squared dx. To be fair, I'll put the plus symbol in black. And then the purple one, we've got pi, the integral from 0 to pi over 2 of the radius, which again we can simplify from up here. The radius was cosine x dx. And that's it. That is our integral expression for the volume of that solid. we could certainly, oh, and I just realized that I missed the squared. That should be cosine x squared. We could throw that at the calculator. We can almost do this by hand. This cosine squared x actually would give us some trouble. But again, a lot of times in these non-calculator questions, they're just going to ask you to set up an integral expression. So keep in mind, if you've got a problem, if you've got a region where there are multiple bounds, it's going to require multiple integrals because there will be different radii on different bounds. So that's the end of this video. I've got one more, so I'll see you there.